Everyone, hello everyone. Today we are going to discuss about Cauchy distribution, and yes, actually we are discussing about continuous probability distributions, and Cauchy distribution is one of them. And it's not only Cauchy but Laplace distribution, beta distribution, negative exponential distribution, and gamma distribution that we are going to talk about today. So, what is a Cauchy distribution? What kind of data are actually distributed using Cauchy distribution? Now, answer to that question is that the data points which are actually more like outliers. For example, if we have a normal curve like this is the position of mu. That is the position of mean. All right. Now, the data points which are actually far from two standard deviation or three standard deviation from actual mean are considered to be the primary factors or primary data in this Cauchy distribution. So you might say this to be a distribution of peculiar kind, or this is also called the distribution of outliers. Okay, so this Cauchy distribution is not that much of practical, but is very important theoretically. Okay, so if we want to talk about the probability density function of Cauchy distribution, then we may write it is f of x is equals to 1 by pi lambda by lambda squared plus x minus mu whole squared, and this distribution lies in between the range of plus infinity to minus infinity. So we can do some arrangement here, and what we can do is we can take lambda square as common, 1 plus x minus mu whole square by lambda squared. Then what next? Okay, so then lambda are cancelled. We get pi lambda times 1 plus whole squared. So this is what the probability density function of Cauchy distribution look like. The values of mu and lambda are always greater than 0 here, and the distribution is denoted by x follows Cauchy of mu lambda. So we can say this mu and lambda, which are non-zero, are actually the parameters of this distribution. So this is about the PDF of Cauchy distribution. Okay, so after this, now we can also define something called a standard Cauchy distribution, and for that we consider this term here. Let me choose a new pen. Yes, so this term here, let's say this to be z. If I say this to be z, then it will be plus z squared, and here the lambda would vanish, and as a result of which we get this, and this is what called as the standard Cauchy distribution. We may say it to be a normalized Cauchy distribution. Now by normalized, what I mean is the distribution would look like this. Such that mu equals 0, that is mean is at 0, and the distribution, the total area under the distribution is 1. This is what I mean by normalization. Okay, so what next? We can find out the distribution function of Cauchy distribution. Now we know the method of finding distribution function when PDF is given, and that is to integrate the probability density function from the in the range. Then we will get that. So uh, okay, I think we should use another board, so let's go there. So let's first write the relation between PDF and the distribution function. Now the distribution function is denoted by capital X. Capital F is equal to, actually the differentiation of is equal to f of x. This capital Fx denotes the distribution function, and small fx okay, I think it's, is it visual now? Okay, yes. So small fx is the PDF. Now we can write it. If you want to find out fx, when small fx is given, we can just integrate it f of x from minus infinity. Okay, so what do you think is the upper limit here, or maybe what do you think the limit of integration is? So we know that distribution function. So if you don't get any intuition of the distribution function, then you can understand it by in this way. So if I have a probability, let's suppose we have probability column and we have distribution column. So probability when x equals 1, something like this, 1, let's suppose 0.9, p of x equals 2, let's suppose 0.8, and so on. So what this probability density function, distribution function does, it just add all the probabilities. It's just like a CF, a cumulative frequency, but for the probabilities. So it adds this 0.9 plus 0.8. In this particular case, the probability become 1. Become 1. Sorry. In the previous case, when I considered this to be 0.8, the summation would be greater than 1, which is a violation of probability rules. That's why I just amend it by making this 0.1, so the total probabilities become 1. Now you can say the probability distribution is the sum, right? So sum up to where? Sum from the, okay, so sum from the 1, x equals 1. That means we have a distribution, then probability distribution is the distribution of probabilities from here to here, no matter what the range is. So let's suppose minus infinity and infinity is, we're talking about Cauchy's distribution, but it says f of x. So now x, this upper limit may be different for different axes. So let's suppose this to be x. Upper limit, let's suppose upper limit to be x. So if that is true, then limit is minus infinity to x. Okay. Now after that, oh, okay, I think I did a pretty much nonsense a lot of nonsense, because if I had introduced f of x equals p of x all the way greater than z x, if I have introduced this relation here, I don't have to talk too much, because if you see this, it says probability of x is smaller than x from x. That means it sums up the distribution function sums up the probabilities of x which are smaller than x. That means x is the upper limit. If I had just written this formula, then I don't have to do this much of nonsense. Okay, so let's forget this, and just from that function we can write the limit from minus infinity to x. Now, what is the function? The function is uh, minus infinity to x, f of x. F of x is lambda 1 by pi lambda by lambda squared plus x minus mu whole squared, right? Wait a second. Yes, so this is the this is fx dx, fx dx. Now minus infinity to x, 1 by pi is a constant, lambda, okay, I think lambda is also a constant, is it? Okay, so okay, what it did is 1 by pi, and it suggests that rather than doing, okay, so uh, yes, so I don't remember where I was, so I would like to dictate from the beginning. So our task here is to find out the distribution function, the probability distribution function, when PDF is given. And for that, we can use two relations in between the distribution function and the density function. First relation is that differentiation of fx with respect to x is equals to small fx, and another relation is fx, capital Fx equals probability of x greater than equals to x. Now this second relation, which is written by red color here, says that this x is the upper bound. That's why we know the lower bound and upper bound of this integral. When this differentiation goes to the other side, it becomes integration. So we know the PDF of Cauchy distribution looks something like this: 1 by lambda squared plus x minus mu squared dx. Now, since it's a very large component, I try to consider this whole term. If I divide it by lambda squared, it cancels and becomes 1, and this becomes 1 by lambda. So I consider this whole term as g, such that differentiation of this with respect to x becomes dx, and this becomes lambda dx, lambda dz. Now after that, I substitute it in here. Let me. So yes, so I substituted here z lambda z equals 1 by 1 plus z squared dz. This is what we got after substitution. Now, the previous limits were minus infinity to x, but since our variable has been changed from x to z, we need to find out the limits of z. For that, I did this process. After that, putting everything inside the integration again with new limits, I get this. After this, we know, actually we don't need to do this. Yes, we know the formula of 1 by 1 plus z square integration of dz. So I use that. That is tan inverse of x. So I don't think that's 2. Yeah. So this is what we get. This is what we get is and after some solution we get 1 by 2 plus 1 by pi tan inverse of x minus mu by lambda is distribution function f of xi. Sorry, f of x for Cauchy distribution. So this is what we got as a distribution function. Now after distribution function we can also find out something called the cumulative distribution function, and this cumulative distribution function is very similar to this distribution function with one nuance, and that is okay, yes, and that is that okay, let's do this. I'll do this again. Oh, okay. So what I understood is that this cumulative distribution function is same as this distribution function, but the main difference is that instead of fx is the instead here the distribution here for finding distribution function, that fx was the original distribution function, original density function, but when we are to find when you are up to find the cumulative distribution function, just use the standard Cauchy distribution PDF and put it there. Then you would get the same, do the same process, and what would you get at the last is the cumulative distribution function. This is it. Now Cauchy distribution don't have any kind of mean, because as we have seen this in the standard Cauchy distribution, the mean in the standard Cauchy distribution, the mean was exactly at 0. So since mean is equals to 0 uh, and it is symmetrical, that means the median as well as mode is 0, and that means we cannot find any moments here. That is the momentless distribution is Cauchy distribution, or we can say Cauchy distribution is a momentless distribution. Now you can check that by, you don't have to do anything for the mean, but for variance you can check it as expectation of x squared integration of x squared fx, and the and follow the uh, process that I just did, and you would get that it would lead to infinity. It would lead to infinity, and that means the variance is very high and moment is at 0, so, and mean is at 0. Okay, so you can write moment of them is mu r dash. Yeah, so mu r dash is equals to expectation of x to the power r, and expectation, since it's a continuous distribution, minus infinity to infinity x to the power r f of x dx. We can substitute that, and we would find that this integral after substituting this fx is not convergent. That means it won't converge, it would be near infinity. So since moment is at infinity, that means we cannot find any, the moment genetic function is at infinity, so we cannot find the moments as well. Okay, so these are some of the characteristics of the Cauchy distribution. Uh, Now let's talk about something else, and that is okay. So what should we discuss now? Properties of Cauchy distribution. I have already said it. Okay, I think this is it about the Cauchy distribution, and let's get to our new distribution, that is gamma distribution. Gamma gamma distributions. Now before discussing gamma distribution, let's write some formulas about this gamma, which are very handy, which will be very handy afterwards. So that is gamma n is equals to minus, sorry, 0 to infinity e to the power minus x to the power n minus 1 dx. This is called the gamma integral where n is greater than 0. This is called gamma integral, or sometimes it's also called as Euler's second equation, beta equation being the Euler's first equation. So this integral is an improper integral which converges to n greater than 0. Now there is another formula of gamma 2 which would be helpful for us, and that is this: n minus 1 factorial gamma n equals n minus 1 gamma n minus 1. Okay, so these are something that you should know beforehand before starting gamma distribution. Now as you know these, let's write the PDF of gamma distribution. The PDF of gamma distribution looks something like this: f of x equals e to the power minus x alpha minus 1 for x lying in between 0 and infinity, and alpha is greater than 0 or 0 otherwise. Now here alpha is the parameter, so we can also write it as f given alpha e to the power minus x to the power alpha minus 1, which exists for x from 0 to infinity. Okay, so it can easily be proved that the function f(x) is a probability density function, and to prove that this function is actually a PDF or not, we can write its proof as following. Now it can be, yes, so what you need to do is you need to integrate it with respect to dx, which is the random variable here, and if you do that, integration of 0 to infinity of e to the power minus x to the power alpha minus 1, then we would get yes, so okay, wait a second, yes, okay, so we would get 1 by alpha sorry, by gamma alpha, by gamma alpha. So by gamma alpha. So this now gamma alpha is constant since alpha is a parameter and 0 to infinity of this thing e to the power minus x to the power alpha minus 1. Now this integral, as we know from the gamma, the previous gamma integral is equal to gamma alpha. So we can cancel these two and get 1, and since the area under the distribution of this function is 1, we can say that this is indeed a probability density function. Now there is another form of gamma integral also in terms of two parameters alpha and beta, and which has a PDF which looks like this: f of x, which is f of x given two parameters alpha and beta, and this is given by beta alpha by gamma alpha times e to the power minus beta x times x to the power alpha minus 1, which lies when x lies in between 0 and infinity, alpha is greater than 0 and beta is greater than 0, 0 otherwise. So this is about yes. Now another form of two parameter gamma distribution is given by this. So sometimes in very rare occasions, we consider beta to be 1 by theta, and you will understand what theta is in just a moment. Can also be written in the form of f of x alpha theta is given by e to the power minus x given theta x alpha minus 1 by theta to the power alpha and gamma alpha. All the constants are same. So this is also sometimes used as a PDF of gamma distribution. Okay, so this is all about the PDFs. Now let's talk about other things. Now, in contrast to the Cauchy distribution, gamma distribution have their own moments. That means the mean, variance, and other moments exist for gamma distribution. So now let's see that and compute the moments. Now we all know to find out the moments, we write mu r dash equals expectation of x. Now expectation of x to the power r. Yes. So there are some nuances. You might have been confused about two things. First one is moment generating function, which is given by expectation of tx, or the moment. Yes. So one is moment generating function and another is moments. Another is the way how you find moments. Okay, sometimes you can find the moments by differentiating this mxt. Okay, This is also an option, but sometimes we directly find the moments in this way. So we have this expectation means integration of x to the power r f of x dx mu r dash. Now what is the range of this gamma integral? That is 0 to x, sorry 0 to infinity. So this is it. Now for simplicity, let's take the PDF which is most used, and that is the PDF which contains alpha only. That is 0 to infinity x to the power r as x to the power r e to the power minus x alpha minus 1 by gamma alpha dx. Now after this, gamma alpha is a constant, so I take it as common. Then after e to the power minus x r plus alpha minus 1, I can write it in this way too. So 1 by gamma alpha, and this whole term is just gamma alpha plus r, right? So this becomes gamma alpha plus r by gamma alpha. So this has become the way, or not the way, but this has become a common function for computing all of the moments. So let's go. Let's start with r equals 1, which gives us mu1 dash, which also stands for the moments. That is mu r dash. Yeah, so mu r dash equals alpha plus r gamma alpha. Let r equals 1, mu1 dash equals gamma alpha plus 1 gamma alpha yes, so alpha gamma alpha maybe. Okay, let me check. I think so. Yeah. Gamma alpha, these are cancelled, so alpha is the mu1 dash. Similarly, mu2 dash gamma alpha plus 2 gamma alpha plus 2 alpha plus 1 gamma alpha plus 1 gamma alpha plus 1 times alpha gamma alpha. Is it so? I think so. Okay, by gamma alpha these are cancelled, so alpha times alpha plus 1 alpha is alpha plus alpha is alpha times alpha plus 1. So this is mu2 dash, and I think I should keep an account of them. Mu1 dash equals alpha, mu2 dash equals alpha times alpha plus 1, and it turns out it's just the sequence. That means mu three dash is this, and mu4 dash is this. Okay, so yeah, so now we have found these raw moments. Let's try to find out the central moments too. For that, mu1 is always 0, mu2 is equals to mu2 dash minus mu1 dash whole squared, alpha plus 1 minus alpha squared, yeah, alpha squared plus alpha minus alpha squared is alpha, and mu3 is equals to mu3 dash minus 2 mu2 dash mu1 dash plus mu1 dash whole squared. Wait, okay, actually it's 3 and it's 2. Yeah, so I get alpha plus 1 alpha plus 2 minus 3 alpha plus 1 alpha plus 2 alpha cube alpha squared plus alpha plus 2 minus 3 alpha squared plus alpha cube alpha squared alpha cube plus 2 alpha squared plus alpha squared, that gives us 3 alpha squared plus 2 alpha 3 alpha cube minus 3 alpha squared plus 2 alpha cube. Okay, 1 alpha cube, 2 alpha cube. These alpha cubes are cancelled. Alpha squared cancelled. So we are left with 2 alpha only. That means I need to keep account of them too. So mu1 equals 0, mu2 equals alpha, mu3 equals 2 alpha, and mu4 equals 3 alpha. Is it 3 alpha? Let me check. Actually, it's not 3 alpha. 3 alpha squared plus 6 alpha instead. Okay, so we can find out the variance from here now, and the variance is given by the variance wait a second, mu2 dash minus mu1 dash whole squared. Is it actually the variance? No, we can just get it by mu2, and mu2 is equals to alpha. And what is the mean? Mu1, that is alpha, mu1 dash, that is alpha. So a peculiar characteristic has been observed, that is variance is equal to mean. This is what we observe for the gamma distribution. What next? So let's find out the moment generation function too. Okay, so let's do that. Moment generating function. Now I have already said the distinction between finding moments by expectation of x and by finding moment generating function by expectation of e to the power tx, where t is a time variable. So integration of 0 infinity etx f of x dx. 0 infinity dx. What is fx? Fx is e to the power minus alpha, e to the power minus x x to the power alpha plus alpha minus 1 gamma sigma times, actually wait a second, yes, so this is f of x, this is dx, 0 infinity e to the power t minus 1x x alpha minus 1, and this is a constant, so we can take 1 by gamma alpha into dx infinity for t minus 1x x to the alpha minus 1. So what we can do expectation of 1 by t. So one thing that we can do is multiplying this and dividing this same thing. Now after that, I don't know either it helps or not, but let me check. So 1 by sigma 1 by gamma alpha 0 infinity, actually 1 by gamma alpha t minus 1 to the power alpha minus 1 times 0 to infinity to the power t minus 1 of x and x alpha minus 1 becomes t minus 1 to the power alpha minus 1. Is it? Yes, I think so. So instead of writing every single time, let's say this to be a g. So it becomes g times 0 infinity to the power, and let's say this to be u. Okay, u times u alpha minus 1. Wait a second, yes, so it becomes u alpha minus 1, is it? I think so. I think it is. So wait a second, yeah, so is it in the form of e to the power minus x to the power alpha minus 1, no, x minus 1, okay, no, it's minus n minus 1. Is it in this form? Actually not. It is not in that form until and unless we take a minus sign there. So that means, let's say this to be a minus with u, and if this is a minus u, then this has to be minus u, and power of that would be a lot of things, but let's say that to be u minus u. Okay, nevertheless we get this, and that gives us z times gamma of alpha plus 1 minus 1, that is alpha. Okay, so our moment generating function looks something like this. G is Let me check either it's wrong or right. Alright. Okay. So this is correct. But okay, what did I do? But somewhere I think I had left this term. If you multiply this term, this gives this. So please see where I did that mistake, and this is this is what we get. S and minus alpha. One minus alpha, and this becomes 0, and 1 minus alpha. Okay, actually that's minus, so that's minus something like that. Okay, now ultimately we will get this term. So our moment generating function is mxt max equals 1 minus t to the power minus alpha. Yeah, so this is what we for moment generating function. Now this moment generating function can be used to find the moments, but I'm not going to towards that because we have already found out a method for finding moments. Okay, and in question and in examination also, it doesn't matter how you find the moments. Okay, the method is not mentioned in the question. That's why you can apply any method. You don't have to go through this because it would be a tedious work for you, and the previous method was an excellent method for doing an examination in that short period of time. So this is about it. So this is all about the gamma distribution. There are some topics that I have left. Actually these topics, okay, let me check this. Yes, this topics has been left intentionally behind because in the standard syllabus of BSc second year statistics, the left topics are not mentioned. That's why I didn't give much preference to them. Now, let's talk about another distribution, and that is a beta distribution. Okay, so let's talk about beta distribution. Now again, before understanding beta distribution, you need to understand some of the prerequisites of this topic, that is beta integral. What is a beta integral? Beta integral, denoted by this, is equal to integration from 0 to 1 of x to the power m minus 1 minus x to the power n minus 1 dx. So this is the beta integral, also known as Euler's first integral. Okay. Now there's a very interesting relationship in between beta integral and gamma integral, and that is as follows: beta mn equals gamma m times gamma m plus n. Okay. Now here let's talk about beta distribution. Now the beta distribution here is distributed or is divided into two types or two kinds. The first one is beta distribution of first kind. Beta distribution of first kind, and the second one is beta distribution second kind. Okay. Now these different kinds are actually based on the distribution, the different PDFs. Okay. And among that, and in that different, in those different PDFs, the approach, what the approach that we followed is different. So let's start with the first kind, beta distribution of first kind. Okay, so the PDF of beta distribution of first kind is that f of x equals x of x to the power m minus 1 minus x to the power n minus 1 by beta mn zero otherwise, and this x lies in between 0 and 1. This beta distribution has parameters m and n, right? So we can write it in this form too: x to the power n minus 1 minus x to the power n minus 1 by beta mn. This is it. Okay, where x lies in between 0 and 1. Now we can easily show that this is a PDF by integrating it from 0 to infinity. No, not 0 to infinity, 0 to 1, because the function lies in between 0 and 1, and if we do so, we would get 1 if it is a if it actually is PDF. Now let's talk about moments of these beta distribution of first kind. Now you may be wondering, why do we always are in hurry to find out the moments of any distribution? And the answer to that is, until and unless you find moments of any distribution, then that distribution is of no use to you, because only when you find the moments of those distribution, you can know about about mean, median, mode, standard deviation, variance, kurtosis, skewness, and everything about that particular distribution. So that's why the statisticians are so crazy about finding the moments of any distribution. Okay, so this is it. So yeah, let's find out the moments moments of first kind. Now I'm not going to say first kind for every single time. You just have to note that by yourself. Okay. Now we have already shown. Sorry. We have already seen. Let me use some interesting color. Yes. So let's use green one. Yeah. So we already know the formula for this. Mu over x equals expectation of x. Expectation means summation if it is a discrete probability distribution, and integration when it's a continuous probability distribution. Since beta is a continuous probability distribution, we are going to use integration sign from 0 to 1 because the function of PDF lies in between this. X to the power r, sorry, actually it's expectation x to the power r. I'm very sorry about that. F of x dx 0 and 1 to power r. Now sometimes some people may get stuck to find out how do we get that limits of integration, and the answer is simple. You just have to see in what domain is the function defined. If the function is defined from 0 to infinity, the limit is 0 to infinity. If the function is defined in 0 to 1, like in this case, the limit is 0 and 0 to 1. X of r, what is what is fx? It is x to the power n minus 1 1 minus x to the power n minus n n minus n minus 1 beta mn dx. Is there anything common? Sorry, is there anything constant or maybe which doesn't involve x variable? Yes, there is. And I have already written this in here. Okay. So I have already written it here, right here. So what do you think we can do next? So we have got up to here. Now, what was the formula for beta distribution? Not the beta distribution, but beta integral. If you remember, which I don't, so I have to pick at the book every single time, is equals to 0 1 x to the power m minus 1 times 1 plus x 1 minus x and minus 1 dx. So we can consider this to be what? Maybe O. Then we can write it as 1 by beta mn from 0 to 1. Yeah, so from 0 to 1 x 0 minus 1. So now not 0 but O. I think this makes a little confusion here. So let's say this to be Q. Q minus 1 1 minus x to the power n minus 1. This is exactly as same as this, just m has been replaced by q. So we can write, so we can write one by beta times Qn, right? Now Now we can use the interesting formula that I discussed about in the interesting relation in between beta and gamma integral, which was given by, anyone remember? Which was given by gamma, what was it? Oh, sorry, beta mn gamma m gamma n gamma m plus n. So let's use that. If I do, I would get gamma m plus n gamma n times gamma q gamma n gamma q plus n. And if I see, I can cancel these two terms, gamma m plus n gamma q plus n is it right? Is it right? M plus r. Yeah, and we know that q are just m plus r. So if I write that, I think I should write it here. M plus n gamma. Okay, actually it's gamma and n plus n gamma. Yes. Okay, yes it is. So this is it. This is about the sorry, not PDF, but what was it? The moment and the function, right? Okay, so this is moments. Now we can find out the information about distribution from now on. And for that, we have to do some other calculations. Yeah. Okay. If I write up to there, you would be able to see it, right? Okay then. So we have this. Now let's substitute r equals 1. Then it becomes mu1s equals what is wrong with this? Yeah, okay, so yeah, so this is mean. So let me take an account. So first entry into this logbook is mean, which is m by m plus n. I think I should write this here too. So it will be mu r dash equals gamma m plus n gamma m plus n plus r times m plus r gamma m. So I get what mu, let's suppose r equals to mu2 dash equals gamma m plus n gamma m plus n plus 2 gamma m plus r gamma m is 2. So what next? Gamma m plus n, gamma m plus n, gamma m plus n plus 1, m plus n plus 1, gamma m plus 1, gamma m plus 1, gamma m, gamma m plus n, m plus n plus 1, m plus n, gamma m plus n, m plus 1, m, gamma m, gamma m, and these are cancelled, these are cancelled. So what I get is gamma, no, none of the gamma left, none of the gamma survived, but we have got some survivors here which are non-gamma terms, and I think this is it. Let me check. Yeah, so we have got this as not variance, still not variance. We have to do something to get variance, but expectation of maybe x squared m plus 1 m, m plus n plus 1, m plus n. Okay, no problem. So what about mu3? We can find out mu3. Yeah, we can find out mu3 and mu4 as well, but that are not much of importance right now, so I'm leaving it to you. Okay, you are going to do it. So okay. So there is some topics which I would like to discuss, but I'm too tired to discuss it, which include mode of beta distribution of first kind. Okay, so what should I do? Let's do it. Mode of beta distribution of first kind. So now for finding mode, every single time you should remember this, you should keep it in your mind that if ever in the journey of your life you have to find out the mode of any distribution, then just differentiate it with respect to the variable itself and equate it to 0, and after that not equate it, but see whether the second derivative is smaller than 0 or not. If such conditions are met, then you are happy, you would have a successful life, and you would find the mode. Otherwise, I mean, there is God for everyone, so he might have some plan for you. Okay, so but I can't say anything. So f of x. So we have f of x equal x to the power m minus 1 1 minus x to the power n minus 1 beta mn. Now differentiate it with respect to f, as if with respect to x. Now this common thing would always be common, and we are left with x minus 1, 1 minus x and minus 1. We have to differentiate it with respect to x. It becomes 1 by beta mn. I don't want to write it every single time I go somewhere. Make it disrespectful, you know. So let's say this to be k, where k is just 1 by, it's rude to carry it wherever I go. So I just set it to be k. Then what is it? So I think I have to use product rule here. That's why I said I won't do it. Okay, so m minus 1 d m minus 1, come on, this chalk, x to the power m minus 1 minus 1, that gives us minus 2 times the same thing, no change in here, then plus this thing has no change here, and differentiation of this would give us n minus 1 times 1 minus x and minus 2. I think it's correct. What do you think about it? No, not until we add a minus sign. I think now it's correct. So I don't think it has any importance now. So I would like to rub it. So why did I rub it? I don't know. So yes, this one equals, what was it? F dash of x, right? Equals k times, is there any simplification that we can make here? Maybe m minus 1, maybe write it with a very good handwriting, x to the power n minus 2, 1 minus x and plus 1. Now plus minus become minus x to the power and this whole term, let's say this to be q. Okay, so we have to set it to be 0. That means the q term x m minus 1 n minus 1, 1 minus x and minus 2, yes, n minus 2 is equal to k times m minus 1. Actually the k is multiplied to both sides, right? So sorry k, but we have to leave you. So m minus 1 x to the power m minus 2, 1 minus x to the power n minus 1. Is there anything that would die for us? I don't think so. I don't know what I'm still doing, but I think this will help. Okay. m minus 1 by n minus 1. Alright, x to the power 1 m minus 1 m minus 2. Alright, what next? Actually, we made a terrible mistake here. Instead of doing whatever we wanted, if we had, okay, not, if we had did something like this, it was minus, so it becomes minus now, no problem, this equals 0. So, yes, so n minus 1, 1 minus x. Alright, so let's write something. X m minus 2, okay, x minus 2. That means, okay, I have to do some things here. First of all, let's make this x minus 2. That means x minus 1, and that means x in here in the denominator. N minus 1 is perfectly fine. Now this 1 minus x to the power 1 minus x and minus 1, 1 minus x to the power minus 1, and again this can be written as 1 minus x, right? Minus n minus 1 x n minus 2 1 minus this. So let's take everything common that can be taken common. One minus x to the power n minus 1 n minus 1x minus m minus 1. This is it. Yeah. N minus 1. Actually, this x and 1 minus x, right? Wait a second. We have 1 minus x here. Actually, it's not. If I say m minus 2, wait. I think I did some mismatch there, but I think I should get x in here, okay? I don't know how, but x is in here. So that would give us x equals 0. Now, since this quantity is not 0, now you may say, why is it 0? Why isn't it 0? Because, again, let me check. Why isn't it 0? So for this whole thing to be 0, either the previous term is 0 or this term is 0. Okay. Now somehow, the reason that I can't remember right now, this is not 0, and that's a fact. Now let's say this, let's set that to 0, and let's see what we get. N minus 1, 1 minus x equals, is it m? M minus 1. I think so. Yeah. Alright. And n minus 1 actually just multiplied with 1 minus x. Now let's find out x, the value of x from here. That means we have to do a lot of work. And m times mx minus plus x minus 1. So go Mr. Minus mx, go. go to the left hand side. So nx minus x plus mx equals no equal, but rather this. So m minus 1. M minus 1, yeah. Then m minus 1 plus m minus 1x dash m plus n minus 2 x equals m minus 1. Then it gives us x equals m minus 1 m plus n minus 2, and this is what we get for the value of x. Okay, now this is the value of x that is at the stationary point, or that is, now this is a point where mode is where, sorry, what I'm saying. So this is the point where the distribution is at its mode. Okay, now it's not actually proved up to now that it exists at mode, because we haven't said we haven't proved this fact. But wait, we know that, right? It's already given there. So since we have this x equals this, now we also have to prove, now it can be shown, okay, it can be shown that f of minus x is always greater than 0. Sorry, not 0, smaller than 0. Yeah, not greater than, but it's more than 0. That's why this is the mode of first, what was it, beta distribution of first kind. Beta distribution of first kind. It was not that bad, was it? For me it was. So this is all about the beta distribution of first kind. Now we have to do the same things for beta distribution of second kind. I'm not going to do it. You are going to do it. Okay. So actually it's both the same, you know. If you know how to write one, or if you know the process, and if you have that amount of memory to remember those hectic PDFs, then you would definitely prove it. Okay. So now let's go to the another distribution, which is negative exponential distribution. Let's go. Hello everyone. So today we are going to do negative exponential distribution, and an exponential distribution is one of the most frequently used continuous probability distribution in statistics. The negative exponential distribution is a special kind of the parameter gamma distribution, of the two parameter gamma distribution when alpha equals 1. The exponential distribution has the most application in queuing theory and reliability theory. Okay, so we are interested in its PMF. So what does the PMF of negative exponential look like? It looks something like this. Fx equals theta exponential of minus theta x, when when x is greater than 0, and theta, is it theta or 0? Okay, it's 0 otherwise. 0 otherwise. So exponential distribution, is it visible? Yes. So negative exponential distribution, f of x equals theta e to the power minus theta x when x is greater than 0 and 0 otherwise. So here the theta is a parameter, so we can write it as theta e to the power minus theta x greater than 0. This is our PDF. Okay, this is our PDF. Again, you can easily prove it that this is indeed a probability density function by just integrating it from 0, which is the lower limit, to infinity, because it doesn't mention up to where it goes. Okay, so this is about exponential distribution. Okay, negative exponential distribution. The distribution function, not the density function, but the distribution function of negative exponential looks like the following: f of x, which is a capital F of x now. So capital F of x is equals to 0 when x is smaller than 0, smaller than equals to 0, 1 minus exponential of minus theta x when x is greater than 0, and 1 otherwise. So this is how the distribution of probability under negative exponential distribution look like. Okay, so this 0 when x is equals to 0, x is smaller than 0, and 1 minus e to the power minus x when x is greater than 0, and 1 otherwise. So again, as previous, we are interested in finding its moments, and the moment can be found by simply writing the equation mu r dash equals expectation of x to the power r. Okay, now since the distribution goes from 0 to infinity, we get x to the power r f of r dx 0 to infinity x of r. What is fr? Our distribution function. Okay, theta or 9 theta x. Alright, after this, after this, 0 to infinity, theta is constant, so we can take theta out of this integration sign. XR. Okay, so e to the power minus theta x to the power r, x to the power r. Let's suppose to be this. If we do so, and again, theta this. Now, is it visible? Okay, so now this is equal to theta integration from 0 to infinity e to the power minus theta x, and actually this theta goes here, theta to the power r plus 1 minus 1 in the denominator, minus 1, and here theta x to the power r plus 1 minus 1, and we give us theta to the power minus, this was 1 minus r minus 1 times integration of 0 to infinity to the power minus x, theta x to the power r plus 1 minus 1 dx. So theta to the power minus r. Now this integration of what does that give us? I think it would give us this. Then it would be this. Is this? Yes. So this can also be written as r factorial to the power r. So we got our mu r dash equals r factorial by theta to the power r. Okay. Now, yes. So now let's find the different moments of it. Let's suppose r is equals to 1. If we do that, mu1 dash equals 1 by theta, mu2 dash equals 2 factorial by theta squared, that gives us 2 by theta squared. Mu3 dash equals mu3 dash equals, okay, 3 factorial by theta cube, that gives us 6 by theta cube, and mu4 dash equals 4 factorial by theta to the power 4. 4 factorial is 4, 3, 2, 1, 6, 4, 24 to the power 4. So, so this is our mean. This is our mean. Now for variance equals mu2 dash minus mu1 dash whole squared. Mu1 dash whole squared. Then it gives us 2 by theta squared minus 1 by theta whole squared. Then it gives us 2 by 2 minus 1 is 1, so 1 by theta squared. This is our variance. Okay. Now notice that the variance does not depend upon x. Okay. So this is about it, about the variance and mean of negative exponential distribution. Now in this way we found the moments. Now let's find moment generating function. Now moment generating function can be found in a similar way by using expectation. But I have already said you moment of x is equals to expectation of e to the power tx, and it can be written as 0 to infinity etx f of x is theta minus theta x, right? Yes, dx. So we have two exponentials, 0 to infinity. So x dx, theta is a constant, infinity. And what does this gives us? What does this give us? So theta exponential of that. So what is the exponential of ax? Integration. That gives us eax by a, right? So it gives us e of t minus theta from 0 to infinity theta. Okay, so where to put theta? Yeah, I want to put 0 and infinity. X, but we don't have any x here, do we? I think yes. Now Okay, what are we going to do here? Oh, actually, this t minus theta is a constant. So we can take it out, theta by t minus theta, and this can be written as minus theta minus t x. Is it so? Let me check. Yes, it is. Then theta by t minus theta times exponential. So if we have a zero exponential, then it will be e to the power 0, that's 1, and if it becomes 0, so it gives us the value of theta t minus theta. Wait a second, actually it's minus 1. Is it minus 1? Let me check. Yeah, because why? Because if you integrate, actually it is not out of integration yet. So when it comes out, it is t minus theta, then integration of minus minus of this would be, yeah, integration of minus of this would be a, actually, wait, okay, so yeah, let's redo it from here. So this is theta, and so now as theta, so integration of 0 to infinity, let's make it like this. Then after this, theta integration of this thing would be minus of theta minus t, isn't it? Theta minus t minus, because so what is the integration of e to the power minus ax? It is e to the power minus ax times this, right? Similarly, we can write, uh, okay, so e to the power minus a is theta minus t of x by this thing, that is minus and theta minus t, minus t, theta minus t. Now if I take it common, then it would be theta by theta minus t, and I include minus e minus theta dx from 0 to infinity. It turns out if you apply this becomes 1, and our ultimate moment density function is this, or we can write it as given by this. Is equals to this. Okay. Is it correct? I think so. You can further written as theta by theta minus t, right? So can we divide it by theta? Yes, we can. 1 minus t by theta. So we can write it in this form too. Now this can be taken to the numerator by this expression. That means moment general function is much suitable when it's 1 minus t beta to the power minus 1. Okay, so this is what the moment is. Sorry, this is what the moment generating function is. Now we can find out the different kind of moments from him. From sorry, not from him, but we don't know his gender. So from it, uh, okay, we can do that. Okay, and okay, so how can we do that? So we have equals, now this 1 minus something, this is an can be written in the series, right, in the summation series, and that is 1 plus t by theta plus t square by theta and multiples of it, right? So t r by theta r. So the moment is given by, the raw moment is given by coefficient of tr by r factorial, tr by r factorial, actually yes, 2 factorial under r factorial, coefficient tr by r factorial, okay, coefficient of this from this series. So we can say that mu r dash is equal to what, r factorial by theta squared, right? Theta, not theta squared, we try to power r, because if you see that r factorial by, okay, r factorial, because wait a second, t by r is 1 by theta squared, right? Okay, let me check. Okay, we don't have these things here, here. We need to find out the coefficient of this, but there is no r factorial, so it goes, so what we do is we multiply this whole series by r factorial by r factorial, and that gives us, yes, and that gives us the coefficient of tr by r factorial, that is r factorial by theta r, which is this thing. Okay, I hope you understand this. Okay, so this is it. This is about the moment generated function of negative exponential distribution. Now let's see interquartile range of negative exponential distribution, and then mean deviation about mean of exponential distribution, of negative exponential distribution, and properties and uses. Alright, so okay, so let's talk about interquartile range of negative exponential distribution. Interquartile negative exponential distribution, and how do we find the quartiles? Just as same as we just as same how we find the medians. Now how do we find the median? We do find the median by, in this way, okay, this is the formula for the median. So I think you are talented enough to guess the process of finding first quartile, that lower quartile, that is f of x 1 by 4, right? Similarly, upper quartile 3 by 4, right? So after having these equations, what we can do is we can use them to find out any of quartile, either a second quartile, first quartile, or the third quartile. So let me solve it here, and I'll explain it to you. Okay, so I did this. This is the first initial statement, starting statement, which you understand up to now. Now what I did is I just integrated it, and we got something like this. Then I applied log function, and this gave us this equation. And then I found an expression for Q1 in this way. So this is the quartile first. Similarly, you can find out quartile 2, quartile 3, and just subtract them and divide by 2. That is what the interquartile range is. Sorry, you don't have to divide by 2. You just have to find out the difference in between Q3 and Q1. So very sorry for that. Now it doesn't say half interquartile range, it just says interquartile range. So you don't have to divide it by 2. Okay, so this is about the interquartile range, and now we will like to proceed towards the mean deviation. Yeah, so the mean deviation about mean of a negative exponential distribution. So mean deviation about mean of negative binomial, not negative binomial distribution, but negative exponential distribution. It is given by this. MD mean is equals to expectation of modulus of x minus expectation of fx. So not fx but expectation of x. Then I put the value of x minus of expectation of x in negative exponential distribution, that is 1 by theta. Then I multiplied it with this. It becomes theta x minus 1. I consider theta x to be y, and by changing the limit I got theta dx equal to theta dy. So I changed it and I got this equation. Now this equation turns out that this on integration by part gives us e to the power minus 1, and this gives us e to the power minus 1. Okay, so that means what we have got is we have got 1 by theta e to the power 2 to the power, yes, this is what we got as the mean deviation from mean. Okay, this is all about it.